Welcome back to lecture 11.3, where we're going to talk about the van der Waals gas and throttling. Okay, so this is the part that mainly appears. It appears a little bit in section 3, chapter 3 of this version. We talked about the Joule Kelvin effect, that was 3.8. And then this is in 7.7. Can't find it. 7.7 is the Joule Kelvin effect for throttling. Okay. And we're also going to talk about 7.8, which we'll do next in lecture 11.4. Okay, so let's recap. We have now, we've done our throttling process. For an ideal gas, our delta T, we expect it to be 0. For a hard sphere gas, our delta T was positive. And now we're going to ask what happens for our van der Waals gas. Okay, so we have an indication that it's going to do cooling because last time in 11.2 we saw cooling for a van der Waals gas undergoing free expansion. Okay, so let's take a look. Now, throttling, what's the key feature of a throttling process? What kind of process is it? Isothermal, adiabatic, yada yada, right? Isochoric, isobaric. No, it's isenthalpic. Okay, so that means that our H1 is going to be equal to our H2. Okay, remember, H is going to be U plus P times V. These are molar quantities, all the small ones, right? And so H, we have to figure out now for a van der Waals gas. Okay, now, how are we going to do that? Well, we know that U is going to be CVT minus A over V. We did that last time. But what is PV? How do we recast PV? Well, let's write our van der Waals gas equation. So this was P. How do I best want to start? Where do I want to start with it? Oh, well, yeah, there we go. Okay. So we said that the van der Waals gas we originally defined as RT V minus B minus A over V squared, right? That is, this term was the next leading order correction in V and decreased the pressure, so the minus sign. Okay, so we can combine these. We say that H is now CVT minus A over V plus, let's just say, RT over V minus B minus A over V squared times B. You can see I can multiply that V in. So this is going to give me CVT plus RT B, B minus B, minus 2A over V. CVT. Sorry, let's take out the temperature dependence. So we'll have CV plus RT RV over V minus B times T minus 2A over V. Okay, so what we really want though is we want to say H1 is equal to H2, right? So we're going to write, right, we had P1 was inside our bottle, P2 was out. All right, so this would essentially be this is in terms of volumes, right? So it's a little bit inconvenient, but we had, let's see, CV plus R V1 minus B times T1 minus 2A over V1 equals CV plus R V2 over V2 minus B T2 minus 2A over V2. At this point we just say, okay, this is complicated, right? I was just looking for what delta T was, right? I mean, I'm happy now that delta T is going to possibly be negative, but how do I actually calculate what it is? Well, in general, this needs to be done numerically. Or, I mean, it doesn't need to be, but it's easier to do numerically. So just say do numerically. Or, there's a nice way to do it graphically. Okay? So that's what we're going to do. We're going to look at these things graphically. And what we mean is on not a PV diagram, but on a TP diagram. Okay. So boy, I wish that wasn't there. All right, I'm just going to nix that one so that we can, if you need it, pause the camera or pause your video and make sure you've copied that down. Okay. So, on a temperature versus pressure diagram, we're going to plot what happens for different gases. So let's start with the ideal gas. We say, well, let's start at some pressure. Let's drop to P1, and let's ask what happens. Well, remember, delta T was 0, right? So these lines were all, if you started at various temperatures, would just follow various isotherms, right? But these aren't just isotherms, these are called isenthalps, right? So these are isenthalps. So the isenthalps on for an ideal gas on a TP diagram are slope 0. Those are the lines of constant h are slope 0. Now, to be perfectly honest, we really shouldn't think of these as lines because lines suggest a reversible process. Really, these are indicators, and they're actually just simply the interpolation of a series of points, right, where the state can be calculated at any one of those points now with the isenthalp, but they're not really technically lines. This is not a quasi-static reversible process. Okay. So now let's look for the hard sphere gas. Well, on a TP diagram, well, we know that if we started at 1 pressure, we would go up in temperature, right? So if we drop the pressure, we increase in temperature. Right? So the isenthalps have negative slope, and the slope depends on material. That's basically how it'll depend on B. Now for a van der Waals gas, if we look on a TP diagram, they actually look like this. So they have a complex shape. You go from P2 to P1. And there's a point there's a curve that hits all the maximums, right? And this is called the inversion curve. So there are nice figures in the book, probably better drawn than mine. Figure 7.2 and figure 7.3 in Finn. Figure 7.2 and 7.3 that show these inversion curves. What we mean by inversion is that here, if I start at this pressure and I cool to say this one, right, I have a negative slope, and hence I get warming. But here, if I start, say, here, and I cool and I drop the pressure, right, I have a positive slope, right? And so I get cooling. So whether or not you get cooling or warming depends on where you are on the curve. So I guess this is section 8.6 of Rex. I have a note in my notes. So if we were to look at this a little bit more broadly, right? If we were to look at a larger section of the TP diagram, okay, it's going to look something like the following. you're going to have some curves, and they're going to look like and so the inversion curve will actually have a well-defined, and if I were to extrapolate this back, right, it extrapolates back, okay? So in these regions we have cooling, in these regions we have warming, but this curve is heading this way, right? And so this point is quite special, okay? So we're going to call it the maximum inversion temperature. So T inversion max. So the maximum inversion temperature tells you a lot about a gas and how it behaves as an ideal gas. Okay? So let's look at what these are for a few gases. So let's call this the T inversion max. Okay, so let's make a little chart. Of course, the units are Kelvin. So let's look at argon. So argon is 723 Kelvin. Right? So what that means is likely you can find a pressure, because this is well above atmospheric pressure, that if we were to do this expansion for argon, we're going to get cooling, right? Unless you're at such high pressures that you're over here in this warming. Nitrogen, 621. Hydrogen, 205. And helium, 51. 51 Kelvin. Okay? So, room temperature is roughly 300 Kelvin. So we can liquefy, we can cool nitrogen, right? But you can see we can't cool hydrogen or helium. So this brings up a very important question of how can we get helium to cool? I've shown you that in my lab, we often use liquid helium. We used to use a lot of liquid nitrogen and a lot of liquid helium, but now we use a special kind of cooler that only really uses liquid helium. So how can we imagine making helium a liquid when, if we undergo this, this throttling process, it's going to warm still, okay? So next time we're going to talk about a way to do this, and it's going to be called the Lindy cycle, okay? So next time, 11.4, the Lindy cycle.